All right. All right, everybody. Here we go. We're looking at graphs of motion, and I'm going to show you some videos that I've made with the smart carts we have, which I'll explain what they are when we get there. So we're looking at constant motion and accelerated motion, and distance time graphs and velocity time graphs for all types of motion. Essentially, is the goal. Pretty lofty goal in an older environment. But how we used to analyze motion was basically with dot graphs. There was a product called a ticker tape timer, and it would often be like a nail on a vibrating thing that would smash against a piece of ribbon tape, a long piece of paper, and it would smash out even space dots for uniform motion, constant speed. It would have different spacings if you're speeding up or slowing down. And so you can probably picture how you could measure the spaces to have the distance measurement literally, and then the time is stamped out in the number of spaces. So this one here, you might guess that this for constant motion here, you might guess that you'd have that kind of line. I think we've done enough that that's obvious. Basically, each interval in time, you have the same distance over and over again. So that's a delta t and a delta d. The rest of it, I think we could probably do the rest as well. This one's obviously going faster and faster. So maybe we'll come back to the rest of these, but really the process for getting the VT graph from this was a big process. We're going to know how to do the process, but we're not going to have to do the process. And the advantage of the really cool equipment we have is that you can spend a lot of time analyzing and understanding the motion, spend a lot of time just like looking at the results and understanding it, rather than spending so much time trying to produce the results. And so the goal is we're going to use smart carts and we're going to analyze uniform and non-uniform motion. So this is done as an activity in an in-person class. So basically I send the students out with the carts, showing them a little bit. It takes like 2 minutes to show how to use them. And then I get them to do physically what would be needed to make uniform motion, non-uniform motion with constant acceleration, and so on and so on. Okay, so you'll be seeing the results, the videos of what you'd see in person here. So the first one, uniform motion with constant velocity. So this is the video for that one. Here's that I've got a pen in my hand instead of a pointer here. Here we go. Just get that full screen here. All right, so the video is playing, I think. There we go. Now it is. So you can see my little toy Jeep, the little video screen there, just pushing the cart at a uniform rate across the screen. Right there, there it goes. And it makes a nice straight line on a DT graph. So if I go back to this, which page am I on here? Go back to this right here. That's what we drew. Okay. So that's the result there, right? So I'm just going to be showing you results, and we can look at more and more how to calculate them. I'll talk a little bit as we go, but we're not really doing it yet. We're just understanding that it makes sense. Okay. So if we're looking for a velocity time graph for this, basically you could picture here that in a time interval, and there's a corresponding displacement or distance that it went, and you can tell it's the same value all the time. And so if you're looking at a corresponding VT graph, then this is what you should expect, this section right here, okay? Because we have a time and a displacement, and we're looking at really the velocity equals displacement over time. And so that is equal to a particular number the entire time. This triangle can go anywhere along there and gives you the same value, right? So in math, your math brain might be screaming right now, be like, wait a minute, that's just slope. And absolutely it is. And that's really the mystery up here. But there's a lot of details to it and a lot of work, but really it is slope, okay? So that's something that we're just seeing naturally as we go through and understanding that these graphs make sense and so on. So we have that one nailed down. uniform motion. Remember this, there's a lot of words going to be used here. So this one's like uniform motion, constant velocity, no acceleration, a lot of words you can use to describe this. And when we go to the next step, we'll keep going here. So I was meant for that not to be revealed already. So let's go for uniform acceleration. But we're going to look at, so we're looking at acceleration. And so it's velocity increasing at a constant rate. So uniform acceleration. And that's, velocity increasing at a constant rate. Okay, so let's see that one. Again, get this thing going full screen here. And so you can see what I have here is this is again an activity in person. Students would be figuring out what they need to make physically happen to do this, right? So for the constant motion one, for example, sometimes students just make the ramp be just tilted enough that friction is balanced by the slope of the ramp. You give it a push, it goes at a constant speed. I cheated and used the Jeep because just really obvious. We're talking about uniform motion. So here I just have a ramp. So you're going to see the cart go down the ramp because the ramp's the same angle the whole way. It's going to be the same acceleration the whole way. So here we go. There I am. Cart. And this, by the way, these smart carts, I said I was going to mention it. These smart carts have sensors built into them. And so it's going wirelessly to an iPad. And it's just really cool software. It makes it so awesome to be able to learn what the graphs of motion would look like for all different types of motion all in one day, really. So here we go. We've got the cart going down the ramp. And you're going to see the graph in real time match in red there. So the only problem is it's not zoomed in well, but you saw that it happened in real time. And then you're going to see me, I'm going to go in and rejig things and so on. But eventually I get it sort of zoomed out and centered nicely and so on. I think I even moved that little run number 1 out of the way briefly there, but it's right at the end of the video. So we have this increasing kind of curve upward like that. Okay. So that increasing curve upward is the result for uniform acceleration. And then when we look at the result on the for the velocity time graph, this is what it looks like. And so it should basically match in your mind here that we have slopes from here, from dt to vt. So let's point out that we have slopes as an overall concept are moving us from dt to vt. And we're going to do that later on. But for now, we're just understanding that the idea makes sense. And the harder part to get our head around is the idea of slopes of tangents of lines. And so there's some math concepts that are built into this physics lesson, right? So basically, a slope at an instant there corresponds to the result for the velocity at that instant. Okay, so we'll see the details of this later on, but that slope number would be this number here, and so on. And if you piece a bunch of those together, we're seeing that it's a nice straight line, which makes sense because this would indicate here along the way in a time interval. So a delta t here, a delta d, or delta, not delta t, it's delta v, right? We're looking at the rate of change of the velocity. Rate of change of velocity. And so that is, of course, what we're calling acceleration. So we're seeing another slope concept, by the way. And again, we're going to be doing this very specifically eventually, but we're talking about from a VT graph to the acceleration value is another slope. Okay, so this is really slope again to go to acceleration. So I'll just put the arrow all the way over to here. This is slope again. And again, we're not doing this yet, so it's nothing to stress about. We're just seeing that it makes sense. Okay, so this as a change, so acceleration, we're going to see later on as a formula is delta v over delta t, but as a concept, it's pretty simple. It's rate of change of your velocity with respect to time. That's what acceleration is. You're speeding up or slowing down. All right, keeping going. Let's look at non-uniform motion. So this one was uniform acceleration, right? This one is non-uniform acceleration. I think it's a motion by accident. So non-uniform acceleration. And we're going to have our velocity increasing more and more. So think about what would you do to make that happen? right? I could have had, I suppose, like a curved track of some sort, but really what I did here, you might have just caught a glimpse of it, is I just had the ramp going to a steeper and steeper angle. And as that ramp goes to a steeper and steeper angle, it's going to be speeding up faster and faster, obviously. So then boom, 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 just get that graph all centered out nice. And you can see, I'm just playing around with the scale there to get it centered nice. I wish it did a better job of that on its own, but it's just something you have to drag and drop the scales. So there's the result for that. That's non-uniform acceleration. So we're accelerating more and more. Okay. So for this one, you're going to see that if you did slopes here, we'd have slopes that would be you'd have like a velocity like a velocity like that, and a velocity like this, and a velocity like this. You can see it's getting higher and higher numbers, right? And so the result is like this. So this one isn't uniform this time. It's not forming a straight line, right? These slopes of there, there, and there are getting higher and higher in a non-uniform way. Whereas the previous one, when we looked at the previous one, we had the slopes here. I didn't mention it last time, but we had slope there and slope there and slope there. Exactly the same looking process. Slope, slope number, slope number, slope number. In this case, they end up forming a straight line because it was from a constant acceleration situation. Whereas this one, really the three slopes, you'd have no idea what they're going to look like necessarily, just from a DT graph. So when we did our, the DT and VT, the DT graph for the Jeep going down the ramp, I think I mentioned, I was like, I hope it's uniform acceleration, but it's hard to say because there's, you don't know what the effect of acceleration would be. Okay. So in this case here, you'd see this picture right here and this picture right here look extremely similar. But the result for the VT graph in this case was going up, up, up at a curve because it was non-uniform acceleration, whereas this one goes up in a straight line. It was uniform acceleration. But from the DT graphs, you can't really tell. Okay, that's just something that's just a fact. You just can't quite tell from just the DT graphs. Keeping going, seeing the motions and seeing the graphs. Hopefully this is, the idea is seeing it and seeing the graph. It helps establish that connection in your mind, hopefully here. So we're looking for velocity increasing, but less and less. And so what's going to happen in this one is we're going to have a cart going down a ramp with a steep slope at the start, speeding up, starting from rest, speeding up, but then the slope of the ramp is going to get decreased as I go. So it's going to be speeding up, but by less and less. So it's kind of like in a car, starting from zero, you have the gas pedal on really hard, and then you gradually don't put the gas on as much. Think of it that way, it might be easier to visualize. But my ramp situation here does that for me. So I've got a ramp, and then I made it less and less slope. Okay, and then we'll see the graph. So again, it's a very similar graph. We've got this increasing number here, increasing curve, right? And if we did slope, slope, slopes, we get a VT graph of it. Well, this VT graph ends up looking like the end here. Eventually I get it all. There we go, about like that. Okay, so this curve, and you're going slope, slope, slope. This one's curving downward, okay, because we're speeding up, but less and less. There's all sorts of scenarios here. We just need to be able to see the DT and VT graphs and wrap our head around what they represent. Okay, this can be tricky, and especially because DT graphs and VT graphs kind of look the same. In fact, this one's not even labeled, but this one was a DT graph. I had to go in and label some of them after the fact. I missed this one. And this one is a VT graph. And so exact same looking graphs mean very different things in some scenarios. Like picture, I had a VT and a DT. So if I had a DT graph like this, right, versus a VT graph like this. So if I did on the fly here, if I had this one be a DT graph and this one be a VT graph, they do not mean the same thing, right? So we've seen already that this one would mean uniform motion, nice straight, nice constant speed. This one would mean you're uniformly increasing your speed. This is accelerated motion. They mean very different things. Okay? These are not equal to one another. Okay? So that's the trick, is you have to recognize these are not the same. Okay, so this is a DT graph where you have uniform velocity or uniform speed the whole time, right? So this is constant motion, or constant speed or motion or whatever, however you want to say it. Like I said, there's lots of ways to describe it. This one is constantly changing or increasing speed. Okay, so it's very important for you to think very carefully about what the graph is telling you or showing you, representing when you're asked these kind of questions. Okay, that's just a leftover from before. So now we're looking at velocity slowing down. So we're going to have velocity decreasing at a constant rate. Okay, so let's watch what I did for that one. Can you think about what that would look like if you're tasked with going into a lab and making something slow down at a constant rate? Pretty easy to do. You just launch it up a ramp and it's going to slow down at a constant rate. Here we go. The launch here, right? There's the launch, and then it just sort of held it at the top. So we just looked at slowing down at a constant rate. So I zoom in on the graph and it looks like that. Okay. And I think in this one, I went ahead as well and added in just to show you like kind of how it works here. You can just add another graph and then you select and you say, hey, let's see the velocity time graph. And unfortunately, it makes you zoom in again. And eventually you zoom in again and you see this result. Okay. So let's go back and look at both of those, record both of those here. So we've got the downward curve because we're decreasing our velocity. We started out with a fast velocity, a fast slope, high slope, going to a low slope, right? And then this result here, this is the same motion. These two, like I mentioned on this one, that just because they look the same doesn't mean they are the same. In fact, because it's dt versus vt, distance time versus velocity time graphs, the graphs have to look different in order to mean the same motion. And so these both mean this uniform acceleration, velocity decreasing at a constant rate. And so put the headings in beside each of them just to make it easier to follow here. I'll just do that afterwards. And now we got velocity decreasing less and less. And so this is a cart pushed up a ramp that's steep at first, but then the steepness is reduced. So it's slowing down, but then quickly at first and then slower by less and less. Let's see that one. So there we go. Launched up, but then it was slowing down a lot. And then it got to a point where it was still going up the ramp when the ramp was less steep. And so it slowed down less and less. And so this graph looks extremely similar, right? Just a curve this way again. But then the VT graph you get, when you look at the VT graph pairing of it, I didn't do the VT graph live on this one. Just escape here. And so that, curve downward kind of thing, same idea as that one. Don't worry about that it kind of got into almost constant motion for a bit there, but curve downward. Well, this one looks like that. The VT graph's like that for this one. So you've got a velocity that's changing quickly because of the big slope, and then it's changing less quickly. Whereas this one was the same change in velocity all the time. Okay, but a curving downward dt, curving over dt, and then this one's straight, this one's curved, right, in the VT graphs. We should be able to understand why for all these things. This one was decreasing more and more. Do I have a video for that one? I don't seem to have that one linked. Decreasing more and more. I just have the result showing there, I guess. So if velocity was decreasing, or say we're going up a ramp, and then the slope of the ramp was increased more and more, so it's going to make it slow down faster and faster. That's what things would look like. And that's sort of the highlighted section between the black lines there. So if you're putting all that together, the little challenge would be to think about like what type of motion would make this graph. We should be able to go through this step by step. And so I've divided it into 3 sections, and you always should too. If you have like 3 distinct sections, this like flat line here, this curve like that, and then the curve like that. Okay, so section 1 should be pretty easy. It's it's a distance time graph. First of all, it's a position. You can't quite see it there, but it says position time graph. It means the same thing. Distance time, position time. displacement time. They all mean the same thing, unfortunately. So this one's at the same spot the whole time, right? So it's stopped. Pretty simple, right? So it's basically uniform motion, but it's a velocity of a zero value, right? This one here, the curving downward, is, it could be decreasing less and less, it could be decreasing more and more, or it could be decreasing at a constant rate. So that's when you would basically need more information, right? So it's slowing down, but it could be less and less or more and more, right? Or at a constant rate. So yes, constant rate, less and less or more and more. I think I might have said that already. This last section here, right? We haven't seen that one yet, right? So the hint for that one is, if you notice, as time goes on in all of these graphs, as time goes on, I've been going in the forward direction. I was at 0.2 meters, now I'm at 0.5. Every single one of these was going forward. So that's the hint for this next section. So all the ones we've seen so far have been going forward. Well, what's this one doing? We're starting at whatever it is there, 0.6 meters, and then it's going to less meters from the sensor, or less meters from the starting point. It's actually going backwards. Okay, so what kind of motion backwards? Well, it's speeding up, because in a unit of time, it's only changing this much. The next unit of time, it changes more. The next unit of time, it changes more. So it's speeding up backwards. But again, it could be constant, it could be less and less, it could be more and more. Okay, one of the things I want to take from this is that from the DT graphs, the details are difficult. You can't see the details of how it's changing. You can just see that it's changing. So, the idea of constant or less and less or more and more changes as time goes on. We need more information. Well, we need the VT graph. Okay, so the VT graph for this one is that. So this should help us figure out what the motion was, right? The cart was stopped for a while, then it went further and further, going slower and slower, and then came to a stop. And then it went back down faster and faster. Well, that's going to be pretty easy to make a cart do that, right? You just launch a cart, give it an upwards velocity, up the ramp velocity. The ramp is going to make it slow down, and then slow down to a stop at the top, and then keep going back down the ramp, keep accelerating, I should say, back down the ramp. So that's what this is. This is the record of it. This is what I've been saying here. So the cart's initially going upward, and it slows down at a constant rate. You see the nice straight line. That's the constant rate right there. Let's highlight that. So slowing down at a constant rate, well, that's because of this section right here. It's a nice straight line, right? That's how we know it's a constant rate. And then the idea of going backwards, right? So speeding up at a constant rate, the cart was going down the ramp. That's the backwards part. And then, of course, it's constant rate again because of the straight line, right? This is also a straight line. Almost writing properly there. And then, so basically we have to just make a cart go up the ramp and then allow it to come back down. And I actually paused. I stopped the cart at the top this time on purpose, because I didn't want you to, I didn't want to give it away here, right? But this would just continue on back down. This would continue on back down. Okay, so I'll show you that video. Ready to go as well. So you're going to see me go over. I'm going to hit the little spring that releases the plunger there and launches the thing forward. You're going to see it go up and back down, up and back down. And you saw it real time there. It went up and back down. That's very obvious on a DT graph. But what's not as obvious is what that looks like on a VT graph. Okay, so on the VT graph, you'll see me add the graph and center things and so on, and eventually get it set up where it's like, oh, okay, there's the VT graph. Okay, so there's that straight line of the VT graph. Matches the motion. So that is it. So that gives you a whirlwind tour. The beauty of a video like this is you can go back and play bits and pieces again, remind you of each of the parts. Based on that, you need to watch it enough times, do it enough times, think about it enough times that you're able to correctly identify each kind of motion. Okay, so each of these has been discussed, some more than others, but DT graphs, notice these are DT graphs, these are VT graphs. and so on. All this stuff is doable based on what we've covered. This one at the end here, again, just identifying motions. This one at the end, there's a missing portion here that you can tell based on this section, from the 10 to 20 second mark. And there's a missing portion here that you can tell what it should look like based on the first section. So that's your first part, is complete the missing portions based on the other graph. And then describe the type of motion, right? So determine or describe the type of motion in the first part, the solid line, and in the second part. These are equivalent graphs. These are equal graphs, same motions. Okay, so let's add in there same motions. Oh boy. All right, same motions there. That's important to realize, I guess, for doing that question. And that's about it. So if you have any questions about that stuff, don't be shy. Make sure to post a question about it, and I'll help you out. Okay, till next time. Talk to you later.